Okay, so picking up part 2 of 6.4 notes here, we left off talking about the escape speed. And again, the escape speed is what's the minimum velocity needed for a satellite to break infinitely far away from a certain body's orbit, right? So from a certain body's gravitational pull, I should say. Right, so the escape speed is the minimum velocity, the minimum speed needed. And in order for that to be the minimum, the final total energy here would be 0. Again, it wouldn't have any kinetic energy left because it's the minimum speed. And then the potential energy, we already know infinitely far away, is going to be 0. Right? So that's kind of where we left off on the last part here. And again, that tells me then that the kinetic energy required has to be equal and opposite to the initial potential energy. So at this point, it's just a matter of kind of breaking this up and solving for the velocity. We know the kinetic energy is 1/2 mv squared. We know the potential energy, so this is a negative, but the potential energy is already negative. So it's negative g m1 m2 over r, right? That's the potential energy that we saw defined in the first part of this video. Right, so obviously the negatives here negate each other, and then if I do a little bit more cleanup, the mass of the satellite doesn't matter. The mass of the satellite doesn't matter. So multiplying both sides by 2 and then doing the square root, I get my escape velocity to be 2 times g times m2 all over r. Right, so that's the required escape speed necessary to break free of a planet or of a body, right, that we're in orbit of. Okay, so again, this is the minimum velocity needed to break free. Obviously, since this is the minimum velocity, anything more than this and it would safely break away. Right? If it did have any more than this minimum velocity, then it would have some remaining kinetic energy when it reaches that infinite location, right? But this is the absolute minimum value needed to break free of the gravitational pull of whatever body it's in orbit of. Right? But anyway, that concludes the last topic in this section of the notes. So again, from here on out, all we're going to see are some examples. They are very tricky examples. I would encourage you guys to maybe try them on your own. But obviously, again, these are tough examples. So if you feel like you get stuck at any point, certainly consult the videos and hopefully they can help you out. But anyway, some good examples to look at, make sure you're comfortable with. Definitely a big emphasis, as we see throughout this section here, on finding energies and taking advantage of energy. But anyway, so example 1, and you guys can read through the entire thing here, but the Earth suddenly stops, the gravitational pull of the Sun pulls it directly inward. They give us the distance between the Earth and the Sun's centers, which is good. And then they give us the Earth's radius, the Sun's radius, the Earth's mass, and the Sun's mass. Right, and they ask us here, I think, or maybe they didn't. Yes, they do. What would be the Earth's speed as it crashes into the Sun? Right. So the malicious Mr. Davis has decided that his evil plan to take over the world is actually just to destroy the world, and he is going to stop it in its tracks and cause the Earth to go crashing into this giant blue sun here. Right. So that's his evil plan. That's his goal. How fast would the Earth be going as it crashes into the surface of the Sun? Right? So we're looking for the velocity at that point. And really the easiest way to approach this, the easiest way is using energies. Right? So as we've seen kind of throughout the first semester and really throughout the entire year, right? The easiest approach is usually using energies because it reduces not having to worry about vectors and not having to worry about some of the more complicated measurements. Right? So I'm going to focus on energies. Well, if the Earth all of a sudden stopped right here, what forms of energies would it have with respect to the Sun? Well, if it stopped moving, its kinetic energy would be 0, right? But it would still have some potential energy based on the distance between the two, right? So if I'm thinking in terms of energies, the initial kinetic plus the initial potential energy would equal the final kinetic energy, which will help me find the velocity, plus the final potential energy, which I'll have to think about here in just a second. Oops, and I used a 0 instead of a F for final. Right, so again, if I'm thinking through, the initial kinetic energy is 0 because the Earth had stopped, right? So it stopped moving. The initial potential energy, well, we've seen that a few times, is negative g m1 m2 over r, right? So there's my initial potential energy. And if I look at the information, they gave me the mass of both the Earth and the Sun, and they gave me the distance from center to center, which would represent my r, right? So I actually have all of those measurements right now. The final kinetic energy would be 1/2 the mass of the Earth, so m1 maybe we'll call that, and then the velocity squared, and obviously we're looking for the velocity. And then the final potential energy would be, again, a negative g times the mass of the Earth times the mass of the Sun times their final distance, so I'll call that r2 just to distinguish it, but their final distance, their final separation. And at first you might think that that final separation would be 0, right? But be careful about that part. The final separation wouldn't be 0 because that r represents the distance from the center of the Earth to the center of the Sun, right? So that final displacement is actually going to represent the radius of the Sun plus, as the Earth crashes into it, the radius of the Earth, right? That's going to represent that final r. So keep in mind that that measurement is going to be what we use. But anyway, at this point, it's just a numbers game. You actually know everything else, right? So if I do look at it right now, there is actually one value I can get away without using, and that's the mass of the Earth, right? The mass of the Earth is in each one of those three terms, so I don't need it. So then plugging in the measurements I know, so negative 6.67 times 10 to the negative 11th is our universal constant for G. The mass of the Sun, 1.99 times 10 to the 30th. And then divided by the initial radius, again, the initial separation there, so 1.5 times 10 to the 11th, equals 1/2 the final velocity squared, which is what I'm looking for, that final velocity, minus 6.67 times 10 to the negative 11th, times again the mass of the Sun, 1.99 times 10 to the 30th, and then divided by again the total radius of the Earth and the Sun together, right? So 6.96 times 10 to the 8th for the Sun, and 6.37 times 10 to the 6th for the Earth, which is just going to add a 0.06 really to that. So it ended up being about 7.02 times 10 to the 8th if I've added those correctly. Okay, so about 7.02, and obviously you have some change here as well, but times 10 to the 8th is my final displacement. So again, at this point, it's just a matter of solving. Do be very careful about how you solve this, right? Yes, the numerators are the same, but there's not really anything clever we can do with the denominators. You do just need to calculate this number, and then add it over and solve. And we should end up with the velocity being about, and I'm going to round this off pretty significantly here, but about 620,000, right? So about 620,000 meters per second. Again, you're going to get something more specific than that, but I'll round it off more generically. So you end up with about 620,000 meters per second is how fast the Earth goes as it crashes into this. Okay, so for example 2, a pretty straightforward example of the escape speed. So a 1,000 kilogram rocket is fired straight away from the surface of the Earth. What speed does the rocket need to escape from the gravitational pull of the Earth and never return? Well, it does sound very ominous there. I hope that this problem is not too ominous. You see what I did there. But anyway, I think this problem, you guys will agree, is pretty straightforward. And again, it is launched straight away from the Earth. So once again, another great pun. But anyway, I do want you guys to be comfortable with where this equation, right, where this comes from. I don't want you to just memorize that the escape speed is the square root of 2g, right, m over r. I don't want you to just try and memorize that information. I would much rather you know where that comes from. And again, the relationship's not that bad. The understanding here is I'm starting with potential energy and I'm starting with kinetic energy. And then I know that that should be converting to final potential energy and the final kinetic energy. And as long as there's no outside forces, which we will assume that it's not impacted by the force of the Sun or anything like that. Right? So as long as there's no outside forces, again, energy should be conserved. The key concept then becomes the final potential energy and the final kinetic energy are both 0 if it's the minimum escape velocity, right? If it's the minimum speed needed to escape the Earth, which by definition is what the escape speed is. So again, my final needs to be 0, and so again, that tells me that the initial kinetic needs to be equal and opposite to the initial potential energy. And as soon as I establish that fact, like I said, this problem, hopefully, in all seriousness, is pretty easy. Because again, as soon as I establish that, I'm looking at basically just this relationship here. Oops, I accidentally squared it. The mass of the Earth can cancel out. So I've got 1/2 the velocity squared equals the universal constant times the mass of the satellite, or excuse me, the mass of the Earth. The mass of the satellite was the one that canceled out. So sorry about that. That's the mass of the Earth and then the radius of the Earth. Okay, so my velocity does in fact equal the square root of 2 times the universal constant times the mass of the Earth divided by the radius of the Earth. And solving for that velocity is as easy at this point as plugging in the numbers. So you do have to take advantage of the numbers that I gave you in the previous problem. The mass of the Earth being 5.98 times 10 to the 24th, and the radius of the Earth being 6.37 times 10 to the 6th. Right? But when I do that, I get a velocity to be about 11,190.7 meters per second. Right, so again, plugging in the values for the Earth there, I end up with that measurement. So I do want to make sure you guys are okay with this. Obviously, if you do have any questions over the escape speed or over using energies and how that kind of works, by all means let me know. I think once you get comfortable with this, it's not too bad, but it does take a little while for you to start to kind of see these problems using energy the way that we are right now. Okay, so example 3 probably be the last example I get in this part of the notes here, and then I'll have to wrap up example 4 in the last part. But anyway, Space Transportation Vehicle releases a 470 kilogram communication satellite while in orbit 280 kilometers, and do notice that's kilometers, so it's 280,000. That was not a very good 8 there, but close enough. Above the surface of the Earth, a rocket engine on the satellite boosted into geosynchronous orbit, which we'll think about here in just a second. How much energy does the engine have to provide? Okay, so the idea here is you've got a satellite that's orbiting around the Earth, right? You've got a satellite that's orbiting around the Earth, and then it releases this extra mass here, right? So that satellite releases another satellite or transportation vehicle, and it releases it to go to a different altitude, so that altitude it will be in geosynchronous orbit, which again we'll recap what that means here in just a second, right? But that's the situation. And so in this case, it's actually not an energy conservation problem. They're asking us how much energy does the engine have to provide in order for this to happen. So I hope that that last sentence makes us think the goal here is we really want to find what is the change in energy, right? That's what I'm looking for. If I can find the change in energy as that satellite moves from one orbit to the other, then I can find the energy required by the boosters, by the engine of the satellite. Right, so that's going to be my goal. So then in simple terms, can I try and find the initial energy, and can I try and find the final energy, right? Now again, you could try to do the initial potential plus the initial kinetic, and the final potential plus the final kinetic. But there's a much easier way of approaching that, right? We saw the equation earlier in the notes here for how do I find the total energy of a satellite. And again, the total energy is negative g m1 m2 over 2r. Right, so I'm actually going to find the total initial energy, the total final energy, and then just compare the two, right? Find the difference between the two. So let's see if we can't do that for the initial situation right now. So again, the total initial energy would be my universal constant, negative 6.67 times 10 to the negative 11th. They gave me the mass of the satellite, which is 470. And then I do know the mass of the Earth, again referencing the previous problem, 5.98 times 10 to the 24th. Over the entire radius, so keep in mind it's not just the radius, so it's 2 times the entire radius, which would be the radius of the Earth, so 6.37 times 10 to the 6th, plus the 280,000 kilometer height, right? So there is my final radius. So when I calculate this, right, plug this all in, I end up getting a total energy of negative 1.41 times 10 to the 10th joules of energy, right? So that's how much energy it starts at. And again, I know it feels kind of awkward that is a negative number, but just get comfortable with the fact that when we talk about orbital motion, everything is going to be defined as a negative potential energy, and therefore most total energy will be negative as well. Okay, so we've got our initial energy. The problem is, if I look at the final energy, well, I don't know the final altitude. And that's where this term geosynchronous comes into play, right? The big idea with geosynchronous, if you recall, is geosynchronous tells us it stays in the same place over the Earth as the Earth orbits. So in other words, they're discretely telling us that the period is 24 hours, right? They're telling us that the period is 24 hours. And therefore, they're giving me a means to solve for the radius. So if I incorporate what we've done in the past, I know the period equation for a satellite in orbit is period equals r cubed over gm. I will trust that you guys can plug in the measurements that we know. So again, the mass of the Earth, the universal constant, the period of 24 hours is seconds, and you should be able to find that that r ends up being, give me 1 second here to calculate it myself, that r should end up being about 4.23 times 10 to the 7th. Right, so 4.23 times 10 to the 7th meter. So then as soon as I know that, I can try and find my final energy by just again doing negative g m1 m2 over 2r and using my new radius instead of the original. And when I do that, I should get about negative 2.22 times 10 to the 9th, and then finding the difference would be my answer. So again, finding the difference here, about 1.2 times 10 to the 10th